Today, I would like to talk with you about imagination supervised machine. It's a topic that I have been excited and passionate about for maybe the past 10 years or something. And I want to share with you what imagination is. It's something that you can think about while modeling AI skills. Before I start, I would like to thank a lot of students that have been part of some of the works that has been developed in this work, as well as collaborators that I'm going to mention in the specific projects. So all of us are aware about supervised learning, unsupervised learning, and semi-supervised learning. In supervised learning, on the far left, we have access to all labels. If you want to train a visual classifier, for example, to classify between cats and dogs. In semi-supervised learning, we have access to some labels, and in this case, let's say we want to classify cats and dogs, and maybe the red points are the dog and the blue points are the cat. We have access to some labels, but not everything. And in unsupervised learning, we don't have access to anything, and we wish to learn a representation where things that make sense similarly are close to one another, and things that are different should be far away. And today, I would like to discuss with you another form of that could be orthogonal or complementary to this form of learning, where it's guided by imagination. So, in what I mean by that is that this. In all these forms, you require data. Whether it's labeled or not, that's a different question. But not one form of learning is that the model itself can explicitly explore beyond of the scope of the object it has seen during training. And this is one of the aspects I want to share with you today. All right. So, and I'm gonna do that through going through different steps: seeing, perception, creation, that's generative models. Driving and forecasting tasks like self-driving cars, how you predict the future trajectory of a car, and a feeling that's more linguistic. So how do you, for example, build machine learning model that takes a picture of a scene of a beautiful city, and it has beautiful buildings, greens everywhere, and a lake, and you can build a model that says that this is a picture of a beautiful city. I can imagine myself sitting by the lake, listening to the birds. And maybe there's no birds in the picture, but you imagine this, and this is an aspect of our human intelligence that I want to share with you today. That is something that we can, if we think about when we build AI, we can build some useful tools. All right, I hope that's put things together. And these directions. So these are, for the sake of reference, this is our set of papers in main machine learning courses like ECCV, CVPR, where we publish some of these works. So this is, if you want to refer to some of these methods, and also in addition to that, there are benchmarks that I've been working on. Some of it I did in the early days when I was doing my PhD. Some of them I developed later. So the first one is related to perception. So if you describe a bird that we have never seen before by language, say that this is a barky auklet, it's a small bird that have an orange beak, and the plumage of this bird is dark above and white below. This description of a possibly unseen class for you may help you imagine how it looks like, and identify it if you haven't seen it before. And the right is our data set that relates to the feeling part. And on the left here, this is an ECCV oral paper that talks about also some of these skills, but in 3D space. Let's start by the first step, imagining to see, and that relates to the bird example we just described. So imagine that you have a bird that maybe some of you know already what this bird is, but if I describe this to, let's say, even a 5 years old or 6 years old kid, and tell him that, hey, there is a bird that exists called barky auklet, and it has a short orange beak, and the plumage of the bird is dark above and white below. That description might help imagine this bird. And if I give him or her these 4 different pictures, it's an easy task for him or her to pick which bird we're talking about, right? Because this means that we learn to generalize or understand unseen classes because we have learned some underlying concepts. We learned what a peak means, what an orange beak looks like. We can compose new concepts from existing concepts we already know about, right? So, and in connection to that and imagination, one of the models that directly explicitly model this notion is generative models. So think about having a GAN model or a generative model that takes as an input that language description of the bird. And we hope that this will synthesize visual generations of that bird that is hopefully in line with the description we just mentioned, right? And the hope is that for every unseen class, we generate possible visual representation for the same bird, so that if we iterate of every possible unseen class, we'll generate the data that does not exist for these unseen classes. It's unseen in the sense that we don't have images, but we have a language description. And if you have a way that maps from the description space to the representation space that can help us tell apart these species from one another, we will have a powerful model for representing or for recognizing unseen classes. Why? Unseen classes. Why? Because we will, for every unseen class, we will generate corresponding data over here. And let's show this picture is show that the representation of the fake data that we generate for every unseen class. And then we have an example of now an unseen class. We want to classify it. What we need to do is just to embed in that space and classify it. It can be just as simple as nearest neighbor classification. In fact, this is what we did in practice. All right, this relates to a paper we published back in 2018 in CVPR, which explicitly does this by having a GAN model that takes an input, this language description, produce visual generations of the input class, and then it tried to trick the discriminator to believe that it's real, and at the same time predict the corresponding scene class. So this is a head over scene classes. The usual practice of this task is that people have access during training to a set of scene classes, based on which you try to learn the relationship between the input text and the visual representation, and another set for unseen classes that you evaluate on. So for example, in this benchmark, we have 200 bird species. It's on a popular dataset called the CU birds. And 150 of these classes are used during training, and the remaining 50 classes are used for evaluation. And during evaluation, you have only access to 50 Wikipedia articles that correspond to these 50 unseen classes. And during training, we use the 150 Wikipedia articles that correspond to the seen classes to learn the correspondence, to learn the mapping between the text space where we describe classes and the visual representation space. All right, why this is important? So in real life, we sometimes encounter, let's say, a bird, and out of nowhere, it might fly away. In other situations, we have actually to fly away, otherwise we could be a meal to this hungry bird, right? The point is that from thinking about this from maybe the biodiversity perspective that the United Nations cares about, right? We care about both the bird and the bear in recognizing them at the fine-grained level. Because we want to count how many species do we have of those, and maybe decision makers can take some actions to protect those species. And the more we have models that are capable of recognizing those classes, identifying them, counting them, and being able to know which one of those that you encounter in real life is something that you never see before. This might accelerate research and maybe species discovery. Hopefully, may this technology be developed that far that it is actually useful. So this is the point. So imagine, for example, this is the kid that just lost that bird. He no longer have a picture of the bird, but he can remember how to describe it. He can just say that I saw a bird, but it looks like this bird has an orange beak. And then he asks this robot that loves the Mother Nature, and then it will maybe the information is not sufficient. Maybe imagine that this bot will ask us more and more questions till it knows what bird we really mean and gives us an answer that we're happy with. And at this point, both the kid will know what bird is this and might look for more information about it in Wikipedia and understand more about it. At the same time, can report, hey, I saw this bird in this in this park in Fremont, or this place in Armenia, or this. So you can also say where you have seen this, and maybe this information can be useful. So that's about this part. There are also further development, but this is the point that I'm trying to share with you in the context of imagining to see. And there are, of course, a series of work that connects to that. Creation is also another important skill, because it's an element of our intelligence that helps us push the development of the world around us, and the fashion industry, which is a $2 trillion industry, the art, which creates our heritage over the years, and some of the movements of developing this, I don't know, beauty over time has come through art movements and inventions that people made. Like, for example, at some point when photography was invented, that shifted artists to shift from depicting the reality by actually drawing pictures for families. That maybe a picture is not just one click away. It could be a 2-hour session to draw a picture of a family, right? And this shifted the artist to invent new modes of expression, like cubism and other things, right? And AI has now, if you heard about AI artists right now, a popular art movement, and artists are using it as a tool, for example, to build new art, and also to create as an inspiration tool in fashion, to create new designs and things like that. So I will start by this talk by Creative Adversary Network, which is a model that we developed back in 2015, which is an augmentation on top of GAN. GAN is one of the fundamental framework for generative models. And the point behind GANs is basically to augment GANs with a teaching signal that encourages the model to go beyond what it has seen during training. So it tries to encourage it to be novelty aware and to sample from that novelty space. So what I mean by that is that you want a model that takes this, that is informed by different art styles like this, and it wants to invent a new style. And I want to encourage it to be more capable of producing things that it has not seen before. So the inspiration is coming when we thought about that, we linked that to how people think about creativity in humans. And this wounded curve is by Colin Martindale. It's depicting the principle of least effort, where the x-axis is novelty and y-axis is hedonic value or likability of an artwork. And this showing that if an artwork is not novel, people may not like the work, but as novelty increases, people start to like the work more and more, but not for too long. When the work is too novel to understand and to relate to things that we understand and relate about, connect to, such lack of understanding will lead to lack of appreciation. And the point is, how do we, with such awareness about how we relate to things, can we build a model that can push the generations to be somehow in this desirable area? If we get an out-of-the-box model like GANs and train it on an art dataset, we choose here WikiArt dataset, which has more than 80,000 art paintings. It is trained in a standard way so that the GIS generator tricks the discriminator to believe that the image is real, and the discriminator is trained to distinguish between real and a fake image. But if we do that, we might end up generating the Mona Lisa again, which is a painting that is from the distribution that the model has learned. And this probably is not what we wish to have as a skill. It could be in other tasks, but maybe if this is the goal, maybe this is probably not what we desire, right? So in order to make the model more novelty informed, we added two simple things. First, we added this awareness of the class label. So we have 20 art styles like abstract art, cubism, impressionism, high Renaissance, etc. And then what we did is that we added to the discriminator a style classification loss. So whenever we feed a real image like the Mona Lisa, we want the discriminator to say that this is real, and the class that the Mona Lisa belongs to is high Renaissance, because we know that the Mona Lisa belongs to the high Renaissance art style. So this is one thing, and it enables the representation space of the discriminator to be more aware about these different art styles. But how about the generator? We're still train the generator to believe that this image is real, like to trick the discriminator to believe that it's real. At the same time, we have a loss that explicitly encourages these generations to be different from what it has seen during training, and we call that deviation loss or creativity loss. What is this creativity loss? It's simply, I want to make this image hard to classify to any class I have seen during training. And how do you quantify that? Entropy. So we try to make the generated image, when you compute its response over this style classification loss, to be hard to classify, meaning I want it to be high entropy.
So here, what was updated, the style or the fake real?
The entropic response is over the style classification. The real fake loss is still real. I want to make the generations real. So, for example, this is an example of of a behavior that we don't want. The Mona Lisa is a beautiful picture, but its response, if let's say this 4 bars defines the art style that we have. We have 20, but this is just for the sake of a demonstration. So this will have a high peak on the high Renaissance style, right? And this is low entropy response, right? Because it's confident. It have a high certainty. So what we did, we wanted instead of something that is hard to classify which style class it belongs to.
I was asking, what is the difference between what was added compared to GAN, to other cell networks, generated cell networks?
Two different, like to compared to the standard GAN is two differences. One is this style classification loss, right? That makes the model. It's also used in some other setting. That makes the model more informed about different art styles. And another thing is during training, encouraging the generator to produce explicitly images that deviates from existing art style by adding this deviation loss. And this loss is basically telling the model, hey, I don't want the images that are here, or here. I want things that are hard to belong to any of those. If these are the seen art styles that I have seen during training.
So this generator has several types of predefined style deviations for generate.
Yeah, the style deviation is simply here high entropy over seen classes. But you can extend the style the style classes in a way that you like.
I like it. It's really cool. So creative. On a sheet. It's actually the first work of art made by AI and we sold it someplace. Sorry, I'm like getting very wrong.
So this art piece is one of the pieces that was generated by this model, as well as this painting. So when we made this work at that time, I think we did in 2017, but maybe in 2018 or something, started to get some attention from here at the HPO Silicon Valley and also MIT Tech Review and other media So later next year, we developed a similar version, but for fashion, to show that this technology can be developed also to impact our everyday life. So in this case, it was, I would say, still, it's not. I would say it's not mature enough to build models and then ship and work it in the factory. But it demonstrates that this model are capable of producing, let's say, pants with extended arm sleeve. So the model didn't see something like that before. It has seen pants and T-shirts, and it learns somehow to mix them up, like mix the the pants with sleeves from t-shirts or something. So it just demonstrates that these tools can be used to explore the creative space of possible designs that the designer has, might choose if he or she thinks that it makes sense or not. All right. So that's what. All right. So this is basically the first two stops. One thing I wanted to share is something that connects these to each other. So we developed 5 years later. We developed a version called Creative Walk Adversarial Networks that was published in the same conference, Competition and Creativity Conference, which is the premier one in this particular area, competition and creativity. We call this method Creative Walk Adversarial Networks. What we proposed in this method is a new deviation loss function that is more message passing in the context of the collection of art pieces that we want them to collectively deviate from existing artworks. How do we do that? So this is to give you an idea. This is the difference between the generations from the earlier version and the later version, and these are samples from the new model. And these are what is in green here for each one of those, the nearest neighbor paintings from the training set, which shows that these generations are unique and are different from what has seen during training. So what is Creative Walk Adversarial Networks? It's an adversarial network that is informed by a message passing, it's by a loss function that operates at the mini patch level. And let's imagine that these blue points are the set of images that the generator produces at the current mini patch. So we want the model to produce generations that are message passing to one another to facilitate better collective deviations against seeing classes, which are depicted here by these three classes, but it could be more. All right. How do we quantify? What? All right. How do we do that more technically? Yeah. So imagine that we have these three classes, right? We compute prototypes. This prototype is that for every class, pick 10 examples, compute its features in the discriminator space, average them, and that will give you a single point for every single class. Is that clear to everyone? All right. So you have one feature representation for every class, which is the center of it, but that is defined by these green points. Where does this green point live? It lives in the last layer of the discriminator. All right. So we first compute these 3 points, and then we have, let's say we have k of those, and we generate in the generator still takes only a z vector. We produce n images, which are the blue points. So we have n k green points, 3 green points, and n orange points. What is the loss function that we added? It is the probabilistic random walk that starts from every scene class, go for a random walk for t time steps through the orange points, and then compute the landing probability over scene classes. How do we do that? We compute 3 transition probability matrices. The first one is from the green points to the orange points. We have 3 times, let's say, n, 3 times n. And then we compute that by the distance in the feature space of the discriminator, because we have those represented as vectors in the last layer of the discriminator. So we compute e to the power minus the distance between every pair. You can think of it simply that we compute the distance between all the green points and all the orange points. That will construct 3 times in the matrix, right? And then you compute e to the power minus this distance, and then normalize by the sum to convert every row as a probability transition matrix from every green point to every other orange point. All right? And then you have a similar matrix from every orange point to every other orange points. That's n times n. So that will help you simulate the steps, the random walk steps, if you go from one orange point to the other, because you go through that for t time steps. And then the last one is n times 3, where you go from the orange points back to the green points. So if you work this out, this will be 3 times n, and this will be n times n, and then this will be n times 3. So this will, at the end, this multiplication will be 3 by 3 matrix. The question is, what does this 3 by 3 matrix mean? Or generally, k by k matrix, because you might have k classes, right? The cell I comma j means that what is the probability that you start from class I, go for t time steps through the generated points, and land in class j. Okay. So what we encourage the model to do is to not to know which class starts from as a deviation signal. So you want the model, if you start from one class, go to the generated the feature representation of the image that you want to be novel. You want the landing probability over sync classes to be entropic. That meaning that you don't want the model to be informed which sync class it has starts from. All right. So, and we have another auxiliary RAS that encourages the model to visit as many of those orange points as possible, but this is just technical details to that, because if the points are far away, the message passing part will be misinforming. It will not inform the neural network to have the desired effect. So visiting loss means that I want as many of these orange points as possible to have an influence in the learning this behavior.
May I ask, what are these points meaning? What are they denoting?
They are denoting these generations that we want to be novel.
Like state of generation.
Yeah, that this generation such that the nearest neighbors of it from the training set are very different. So we did this on top of style GAN 1, style GAN 1 and style GAN 2, because this loss is orthogonal to whatever architecture you choose, right? So we have style GAN 1, we have style CAN 1, which is the CAN loss that we described earlier, and the style QAN, which is the new model. And this is showing how people like it in a 1 to 4, 5 ratings. This means that the new model has much more ratings of 4 and 5 than baselines that uses a different architecture without this loss. All right?
So the results were assessed by human.
In this case, yes, that's true. That's right. Because the point here, if you look at, for example, generated models are typically evaluated by FID score, but FID score is just measuring how good the model is fitting the distribution that you train on. It's not a good metric to evaluate the novelty. So we did this, and we also did another evaluation on with depicting here the nearest neighbor distance. Like if every one of these points is, let's say, a model or an evaluation set for a particular model, and we compute here the nearest neighbor distance. So we have a set of images for every model that we generated. We compute its distance from its nearest neighbor to the training set, and we use that nearest neighbor distance as a novelty score, as a quantification of novelty. And we have the ratings, so we can depict in the y-axis how much people like this. And this will show that, for example, that the model that we propose have tried to produce generations that deviates from the training set, and hopefully have better likability. And if you look at this, it actually depicts the one-dot curve that we talked about earlier, right? The desirable influence, right? So one aspect that we wanted also to evaluate is the constructed emotions. How capable this novel generation of constructing emotional experiences for people. So this is a work that we did in CVPR 2021 called Artemis Affective Language for Visual Art. We collected a data set that on artwork where we asked people how you feel, let's say, how you feel about this art piece, and then they make a choice if they feel amusement or contentment, disgust, fear, etc. And then we ask them to write a sentence why they felt that way. So we ask them, hey, what emotion has been constructed if you look at this painting? And we choose the painting space because paintings and artworks are designed to construct emotional experiences for people by design, right? So we did that for an earlier project. I'm gonna refer to this later, but we wanted to see also this. We did that on artworks, and we collected this 455,000 language utterances on 80,000 artworks. But what if we do the same thing on generated works, generated artworks that are produced by this model? What would be the distribution of constructed emotions by people? And that was the distribution. So this means that for these generated artworks, 9% felt excited, 7% felt amused, 19% felt contentment, and 16% felt scared, 12% felt in awe, 11% felt disgust, 1.5% felt angry. All right. So and there is 13.3% felt confused that maybe these images doesn't mean anything. So, but this basically shows that the more than 85% of generated paintings are capable of constructing emotional experiences for people, that people choose it and also justify. We ask people to describe on the generated artworks, so you can see that people say things like in like fear, like car, dark, fear, figure, ghosty, and in excitement, red, peace, like sadness, gloomy, like amusement, attractive, funny. I don't know. I keep, and these are some responses. So there are some pieces that are generated where people related to a beautiful sunset piece, and this is a picture that relates more to ancient Egypt. This is a picture that says that the fetus is like a baby inside a beautiful view. This is a bit more ghosty kind of picture. So you can see that this shows that there is some progress, that AI artwork can construct some meaningful emotional experiences for people. All right, all right. Another connection I want to make is that some of these, there is a connection between imagination to see and imagination to create, and this is the goal of this next stop. So if you look at the one-dot curve that we talked about earlier for generating unseen things, right? But if we try to reinterpret it for the purpose of recognizing unseen class, zero-shot learning, the task we talked about earlier. So we have a paper at ICCV 19 called Creativity Inspired Zero-Shot Learning, which is trying to reflect on this notion of creative generations, but from the perception perspective, to encourage the model to be more capable of recognizing classes that has not seen before. If the bacteria in the y and the x-axis is novelty against seen classes, and the y-axis is generalization, meaning the model's ability to recognize and tell apart unseen classes that are very similar to seen ones. For example, this is a Barkid-Oakland class that we talked about in the beginning of this picture. It has an orange peak, it has the plumage, it has dark above and white below. And this is a possible unseen class, Barkid-Oakland, which is very similar. It has the same orange peak, it has a similar plumage color, but it's different that it has curved feather that comes from the top of the head, right? From the way you describe that class in these two classes in text, they could share a lot, right? And maybe you have seen only one of them during training. So how would you encourage them all to be more capable of understanding these subtle differences, so that at this time you would be less confused about telling them apart? So, and this is what this is about. Oh, I'm sorry. So we added a loss function to the earlier model that we talked about in the beginning of this picture, that tries to explore the possible unseen space in the text space of unseen classes. So assume that we have TH, where TH is a hallucinated unseen class that tries to explore what is a possible unseen bird, or what is a possible unseen animal. And then we feed that to a generative model that aims to depict that what are the visual generations of that hallucinated unseen class. We want that to be realistic, so we want to trick the discriminator to believe that it's real, but assuming that this is a hallucinated description of an unseen class, one thing we need to inform this neural network about, that this is not, this should not belong to any seen class. So this, because this is a visual, this is a generation of a hallucinated unseen class. And we have here a classification head over seen classes. So what we did is that we encouraged this model to have a high entropy over seen classes, meaning the generations that comes from the descriptions of hallucinated unseen classes should not belong to any seen class. So prior art at this moment was only using seen class descriptions. And what we wanted to make the model more explorative of possible unseen classes, so it has an improved ability to tell apart the classes that are very similar like that. All right. Then the question comes, how do we define TH? This is a very good question. We did, and we think we did with something simple, and there is a better way to improve this. But what we did is that we picked two descriptions, two unseen class descriptions in the feature space, two seen class description TA and TB. So TA and TB are two seen class descriptions, and then we picked uniformly an interpolating factor alpha between 0.2 and 0.8 to interpolate between these two, and that was a hallucinated description. What is the intuition behind that? Is that this unseen class usually visually not too far from the seen one, right? So you want to explore something that is not too far from seen classes, because we want to make the model capable of recognizing unseen classes that are within the neighborhood of seen classes, and in that sense, that was an okay assumption. All right. In practice, we measure these particular classes that we talked about and the model's ability to distinguish between them has doubled by only having this additional loss function. Everything else is the same. we implemented this on 7 benchmarks on the main paper, but I think you got the idea. So they improved consistently over 7 benchmarks on both text-based zero-shot learning, which is the description of these classes in language description, or attribute descriptions as well. This is another way to represent classes, seen and unseen classes semantically. We have a work in. I would say we almost we finished this work, and it's currently in submission, called the imaginative walk. It's related to the creative walk paper, but it tries to push this to use this deviation signal for the same goal, for the zero-shot learning goal. So we have these centers but these centers, instead of representing art classes, it represents scene classes and these centers are generated by sampling, by having a condition-generated model that takes the class description, generate a bunch of those, and computing its centers. So we have these green points generated like that, and for unseen classes, we generate the generated points in the same way. We give a hallucinated class description, we sample different Z, and we generate these red points. And the creative walk class that we talked about earlier, we just apply it as is here. So we have 2 modifications. Modification number 1 is that the generator is now conditioned on the text. It's more semantically guided. It's this semantically guided versus averaging a feature representation of 10 images per art style. In this case, we generate the feature representation by a generator, so that this generator is and this representation space is more aware of the visual semantic relationship between the text and the visual representation. In the case of artwork, we don't have text, right? If you remember, right? And we applied the same loss function. And what we found in a zero-shot learning setting, we did this in a more complicated version of zero-shot learning called continual zero-shot learning, where your distribution of seen and unseen classes shifts, dynamically changes over time, but it's zero-shot learning at the end. And the performance improved by a good margin. Like in some data sets, the margin gets to, like, this is in zero-shot learning, and in continual zero-shot learning, the performance, you can see like sometimes it's 3%. In some other cases, actually much higher. Like in this case, 27. The closest runner-up is 21, so 6% improvement. Yeah. So this just shows that how, like, the merit of the story is that how you train machine learning models that tries to think about the possible space of future unseen classes that you haven't seen yet. Because in practice we lifelong learn, right? What we know today is different from what we know a month from today. All right. So this is what we did. We have another paper at ECCV in zero-shot learning, but it tries to recognize at the scale of tens of thousands of unseen classes using ImageNet 21K, but it tries to use some hierarchical structures so that it uses the hierarchical representation of the ImageNet to just encourage that, let's say, the class representation of the parents should be closer to the children, and maybe if you sample something far from here, these two representations should be far away from one another. So we integrated a loss that is informed by ImageNet hierarchy to make the representation space of unseen classes better, and the performance, like using the same feature space, almost double the state of the art, I guess. Like 53%, here 32%, 24%. The best state of the art was 9%. So we are showing here that this is this effectively leveraging the hierarchical information in ImageNet helps improve the representation quality of unseen classes. The metric is zero-shot recognition performance, like how capable the model is of recognizing unseen classes. It's a classification, but at this time you have the class represented by the class name, a text prompt of the class name, like similar. Do you know clip paper? Right. It is the class is represented by the clip representation, right? The text prompt. And I think we have also tried some ideas with learnable prompt. We have tried that on clip and Word2Vec in the paper, and all these methods were based on the same like representation for fair comparison.
How was the hierarchy? Sorry, can I ask a question?
Yeah, sir.
How was the hierarchy inserted into the training process?
But by encouraging the representation of, contrasted by contrastive learning. I want to sample classes, like for each one for each level, I sample positive for every anchor, positives, and these positives are children, and negatives means like this one with this one should be far away from one another. We have the loss function iterates over all levels. And there are appellations in the paper that tries to see like if you do this in this level only, what happens and things like that. But we found a mix between different levels, like it is the one that have the best performance. Right. Driving. This is a small stop where we also show that this kind of hallucinative like behavior can improve and augment the representation in the motion forecasting task, where you encode the history of an ego vehicle car, the self-driving car, and the surrounding vehicles in a feature representation, and you want to predict the future of the car. At an intersection, the car has multiple possible futures: turning to the right, going straight, turning to the left, right? And the Z here represent the multiple possible future, and it is represented by a discrete latent variable, where let's say class 1 go right, class 2 go straight, last 3 turn left, go right first lane, go right left lane. You don't explicitly model name them, but you have a discrete latent variable that hopefully will learn these latent classes. What we did is that we added a discriminator that makes the model capable of predicting which latent class is used to predict the fault trajectory. So we predict sample a driving intent. We predict the whole trajectory. We put it in a map. We feed it to the discriminator. We want the discriminator to tell apart which intent is used to predict that trajectory. And that's made the model more capable of telling apart different driving intent from one another, to making them different. The other loss function is called the hallucinative intent. What we did is that this model is autorecursive, so it predicts. You can set the driving intent at every time step. And instead of having this fixed for all the future, for every next XY coordinate, so you want intent number 1, we feed them, the typical practice is to feed them in all different steps. So we pick a random step, and then we switch from intent number I to intent number J. So and we feed that to the generator. That will produce a trajectory with a mixed intent, right? And we encourage the model to not be capable of classifying which latent intent it belongs to. And this improved the performance of road boundary violation and final displacement error actually significantly. So the final displacement error, like how close the generated trajectory from the ground truth, reduced by 27%. And the road boundary violation means how capable the model is, how frequently the model hit the road boundaries. So that was reduced from 19% to 9%. Okay, so we have now discussed the three main stops. For imagining to see, we talked mainly about 2D space. We have at this ECCV a paper called 3D Compact Composition of Materials of Parts of 3D Things. It's a data set of 7.2 million stylized models of unique compositions. And this means that we have, let's say this is chair. We have a stylized compositions of, like, let's say this is a wood, this can be metal, the seat can be like a rubber, it can be leather, it can be just wood, etc. Right? So we collected this data set. It took 2 years to actually build. We did a lot of mistakes and to ensure the consistency of part namings across different categories and things like that, because this can be a huge mess in evaluation. So it took a lot of time, but eventually it get to a stage that we think can be satisfactory, and we are releasing the dataset for academic use. And the dataset is composed of 7.2 million models, and they are available for every one of these 3D models. We have 8 views, 4 equally spaced views and 4 randomized views, and 990 composition of this is of 7,000 unique shapes. This means that we have for every unique geometry 900 possible different variations of the assignment of materials of different parts of 3D objects. We have 43 shape categories, 167 materials. For every object we apply different materials. In total, we have 58 million renderings because this is 7.2 million models times 8 view for every model. And we have the actual geometry stylized also as well. So so we got a grant from the open data sponsorship from AWS. So the data is about 80 terabytes, but with the help from AWS, we will be hosting it on there. It's already there actually. We are just working on improving the accessibility of the code.
What kind of data you collect? What kind of things there are? After everything only chairs or
43 categories. It's chairs, it's tables, it's cars, it's bicycles. I think there are some canopies. There are. I think. Let me see if there are more examples. Lamps.
So mainly household things.
I think you can think of most ShapeNet classes are there as well. So but the key difference between the dataset and ShapeNet, for example, is that the material part and the composition of these, and also that we are capable of defining new tasks. We define a task called the dataset called compat. We define a task called grounded compat recognition, which is a task of collectively recognizing the shape category as well as the part material pairs that exist in the given model and where they are. Grounded means that I want to know where precisely in the image or in the 3D model this exists. And we proposed metrics for like some baselines that can take the geometry, process it either in 2D or 3D, and predict the part material pair and where they are given the geometry itself, right? And we defined like metrics for that. So shape accuracy is a standard, just classifying how good the model is in recognizing accuracy. Value means the ratio of part material pairs that we recognize correctly in the image. Value grounded is a value of, or is a ratio of part material pairs that we detect in the image, and the mean IOU with the ground truth is more than 50%. So we ground it correctly in the image as well. Value all means that an example is correct if all predicted part material pairs are correct, and I get no score otherwise. Value or grounded is the same thing, but I have to also tell where it is in the image or in the 3D model. All right, this can be capable of, be helpful to also improve scene level tasks, like we can describe object in 3D models by hey, I want the shape that has the metal legs or something. All right. I think the last thing I wanted to share with you, imagination to feel. I already talked to you about this already. Like it's an Artemis. This is a work in 2019, 2020. I was like visiting faculty at Stanford, working with Professor Gepes, and we worked in this project together. Partnership between KAUST and Stanford and the École Polytechnique. And we did this paper. It was inspired a lot from psychology and how we feel about things. And we wanted to make progress on building models that are more, AI models that are more emotion aware, and that is in a visually grounded setting. So we want the models that can tell, hey, this is a picture of a beautiful city. I can imagine myself sitting by the lake, like listening to the birds and things like that. So yeah, so this is basically the emotional aspects. We want to, we talk about, I think Stuart Russell's talking a lot about human compatible AI, for example, from Berkeley. And one of the aspects that we want the model to be more, AI models that are more compatible with human, is to make them more aware of our emotional beings, and maybe this direction is helping moving some steps in this space. So we did last year Artemis 1. We found that there is bias in the dataset because there was much more positive emotions than negative one, and then we say that it's okay not to not be okay. We want the model to be more capable of also negative emotions. So we created Artemis dataset version 2, which is about this, and we collected a dataset that mitigates this bias. So we observed also some generic captions in the dataset, and we wanted to get rid of this. So this is the dataset after balancing it. I'm just showing you the end results. This also helped the performance score improved by 20%. If you use the same size of the data, and 73% of human evaluators favored the models by Artemis 2 than Artemis 1. Then the question is, what happened? Like, what did we do to make this work? We built a data set so that we have many more similar paintings that have opposite emotions. How did we do that? What? We have a video. Okay. Oh, well, this is just to show that this is a Netflix series. It was about 3 people that went through hard times, and they wanted the story of it is they wanted to heal each other emotional ones, And the connection to our title is that we want to do the AI perspective. What we did is that we picked for images that have we ranked the images based on their emotional dominance, so positive or negative, and we know that this is a negative emotions. So we show participant 24 nearest paintings, and then we ask nearest neighbor paintings that are visually similar to this, and then we ask participants, do you think any of those nearest neighbor paintings may construct an opposite emotion? And then if it is, then they click on this and they get directed to either a positive only interface and a negative only interface. And hence we can, if you can imagine that if we do this by iterating on these images, we will balance the dataset bias. Right? And this is this is an interface that we built, and you can see that you can hover and look at things to make things easier for the participants. So this is the story of Artemis 2, and the dataset is available for some other things that are related that to conclude with is that we also, this is a paper for CBPR called Visual GPT. It's about affective captioning. It was about standard captioning, and the goal for it was to use GPT model, to pre-train GPT model to make the model, to make captioning task, which is a task of text to image, data efficient. Learn from, we talked today, like there is one lecture today about data efficiency, like low resource language and things like that, right? So this can be helpful for applications like predicting, generating medical report and things like that. And the model, by distilling the knowledge properly, was using only 0.1% training, 0.5% training. The model was much better than the baselines. Why this can be useful? Imagine the multilingual perspective that we talked about earlier. So some language, we have much more data than others. So if we want to have a model that is capable of producing effective captions similar to the Artemis-like thing, right? So we might not be able to iterate on all possible languages. So we want to integrate new language very quickly to be more inclusive to all possible languages. By the way, we actually collected a version, you can think of this as Artemis 3. It's currently under review. We collected almost a full version of the data in Chinese and also in Arabic. And the difference is that the model, we have data right now that can tell for every painting what is the distribution of emotion from people from English-speaking culture versus Chinese-speaking culture versus Arabic-speaking culture. So you can also study like cultural psychology or cross-cultural psychology with this new ground. We aim to release this data set as well. I think there are some other work that I would say could be less interesting. And we did some work in generative modeling, style GAN-V, that to build models that produces videos and images. We can imagine that we want to build also maybe text-to-image, effective text-to-image or effective text-to-video that helps people maybe construct a particular experience that based on a particular description that the person might be interested. These are some examples. And these are the references, the data set, and thank you. And I'm starting to work actually in a book about this space. Hopefully, but in a year I will have some progress. But yeah. Thank you.
Guys, let's look for the Q&A session. Questions. Please also speak out loud. It will help us to record the questions as well. Thanks.
First of all, thanks for the very inspiring talk. And I'm wondering whether, so you mentioned that you try to have new images that are different from the 20 known styles. And I was wondering whether you in any way also quantified how different these generated images are from each other. This is the first question.
This is.
Do you see any new styles or like clustering of new images?
There is. I think this is the digging a little bit deeper into this is of course interesting. there is a paper that we aim to submit to PAMI in the next couple of weeks that is about this question. So the answer of this question is maybe a 14-page paper. But, but
you mentioned that people rated how they like different images, and like you had some kind of novelty score for this image.
yeah, I'm trying to get. I'm trying to get to this. Yeah, go ahead. One aspect of the analysis that is already there here already is the diversity of emotions, right? So you can actually analyze that. Hey, these are the range of words that people use to describe the generations, right? So 19% is constructing contentment, right? It's I don't know, the 16%. So this is an aspect of the analysis, and that shows some differences from the emotion side, right? There are some aspects that we are in the paper that we're currently studying. We're trying to also to see how there are principles by Wolfland, like who did put together 6 principles to analyze art history and how to analyze them versus, like, for example, linearly versus painterly and some other things. So we collected data set on 1,000 paintings of these Wolfland principles that are usually used to look at, analyze the history of art. And we're trying to do that use that as a tool to evaluate the differences between real art as a distribution and the novel art that the machine learning model would produce. But this is a right question, like.
Yeah, thanks. The reason I'm asking is also because you could use this kind of tools to understand how people generally perceive art. For example, because it's not that people seem to like symmetry or certain color combinations. So I think one could also look, apart from the novelty score, into certain features of the generated images and whether those are more liked by people.
Yeah, like this is a very good. And for example, if you look at the red color, for example, red color is in stock market in the US, right? Green is good, red is bad, right? In China, red is good actually. Like when the stocks are red, it's good, right? So people perceptions of different. And we expect, for example, the red color in the Chinese collected data we talked about may be more pleasant, appears more in weddings and things like that. But maybe this is not the case for other cultures. Yeah. So, yeah.
So what's your viewpoint about will all these AI-generated beautiful pictures and videos will be explicitly indistinguishable in 2-4 years from the reality? I mean, development of these all technologies, GAN and the CAN and so on, etc. They will.
I think some of them are already are indistinguishable with today's thing. We have seen impressive performance by DALI and Imagine. I think there's already more progress on this. One of the things that I feel is less understood is most of the current evaluation is not looking explicitly how we quantify and how we measure these different models in terms of their ability to create new things. And how much it produces, how much from what it produces in a good quality is informed by producing things that are in the comfort zone, meaning it's close to a lot of training data that they have, versus it's really composing new concepts. And I think there are some good qualitative examples, but it's the comparison between different models and benchmarking these skills seems to be still, to me, feels like still an open question.
Okay, so I think we're out of time. The last question. Can we go to the slide with recovering that curve? I forgot the name of the curve.
The one in for art or for perception? For
the one that you had on x-axis the closest neighbor.
Okay, I believe you mean this. Yeah. I believe you mean this.
Yeah. So on x-axis you have the closest neighbor from the generated image to the training set. Right?
True.
And what is that distance? In which space do you?
Good question. I think we did that in the VG G space because it's usually used for style transfer. It's a good model to represent the image.
The network that you use, it's a different space.
Yeah, because if we do that, it will not be standard because every network of those learn its own representation. So you want to standardize the way based on which you measure novelty, right?
And is there a reason that there is a gap between, I don't know, 0.11 and 0.15? Like there are no points.
Because here it's like let me explain maybe in a minute. So in order to evaluate every model, we first generate 10,000 paintings, and then we define 4 groups. There is the high nearest neighbor, the low nearest neighbor groups are the lowest 100 paintings. The high nearest neighbor groups are the farthest 100 paintings. The R is a random group, which is then 100 pictures picked at random for that model. And there is a fourth one called the high entropy group, right? And so this will produce 400 images for every model, okay? And then we see how different models work on the nearest neighbor versions, on the high nearest neighbor versions, on the random versions, and maybe the and if you look at the nearest neighbor version, the nearest neighbor version of Quan is farther from Can. It's more distant, right? And there are different versions that are like high, also have a high likability. So the point that this is trying to show that within the same set, this model is capable of producing things that looks a little bit more novel.
And the y-axis is human evaluation.
Like human evaluation. So this is like this is computed. This is human evaluation.
Okay.
So for now we just measure this and also the constructed emotion as a way to analyze what's going on.
Okay, guys. Good. Thanks, Mohamed, for the great talk.